Okay. So we have the coordinate of the vertex, so number 3, the x-intercepts. Well, we know that the x-intercepts are determined when y is 0. So then we have negative x squared minus x plus 6 equals 0. I recommend, it's up to you, but I will always refuse to solve a quadratic equation or any equation with a negative leading coefficient. So I will multiply both sides by -1. So this is x squared plus x minus 6 equals 0. And then I will factor into x plus 3 and x minus 2. If it takes too long to factor, then you can use the quadratic formula. Okay, so there are two options, Sx equals -3 and x equals 2. So we have two ordered pairs, -3, 0 and 2, 0, that are the x-intercepts. Number 4 is the y-intercept, and this is always easy because it's x equals 0. So when I plug in 0, 0, 0, I get 6. So then y equals 6, so the ordered pair is 0, 6. One thing I would like to mention after I finish this about the x-intercepts, because they may exist or may not exist. So number 5, it's the axis of symmetry, which is, since the vertex is -1/2, 25/4, this is always the case. X equals -1/2 is the axis of symmetry. The vertical line passing through the vertex, axis of symmetry. And 6 is the max-min. Max or min, in this case it's a max, and it's this value, always. Always the y-coordinate of the vertex gives the max or the min. So y equals 25/4 is the max value. And I do have number 7, which is the range. Can anyone give us the range for this function? Can you picture the graph already? It has a maximum, and the maximum is 25/4. Yes, Jack, you can enter through your cell phone. I'm sorry, if I can't see you, I have to get to know you before you take a test. Otherwise, I will not know who's taking the test. So if your camera doesn't work, turn it off. I'll help you with that, and come back with your cell phone. Thank you. Okay, the range is clearly -∞ 25/4. Now we put all this information together and we are ready to graph it. We will start with the vertex. The vertex is at -1/2. So if this is -1, this is -1/2, and 25/4 is a little bit more than 6. 1, 2, 3, 4, 5, 6. A little bit, just a quarter, right here. So I start with the vertex. That's the vertex. Then I continue with the axis of symmetry, which is x equals -1/2. Then I plot the x-intercepts. Where are my x-intercepts? -3, -1, 2, 3, and 1, 2. These are the x-intercepts. Oops. And the y-intercept was 0, 6. 1, 2, 3, 4, 5, 6. And now I'm ready to graph the function. And here it is. Connect and extend. Make sure it's not too sharp at the vertex. Obviously, the domain is all real numbers. We shouldn't even mention it's a polynomial function, but you may be asked to. And the range is from -∞ to 25/4. And this is a complete step-by-step situation. When we determine everything. Step by step. Shape, vertex, X and Y intercepts, axis of symmetry, max min, and range. Now, I would like to make a quick comment on X-intercepts. So our situation was a maximum, so it applies to the minimum as well. But let me just give you the idea. So a maximum for a quadratic function can have three possible options. Here is one option. Here is the second option. And here's the third option. I'm going to connect these to the quadratic formula as well. I'm going to copy the quadratic formula here. And what's the connection? There is a big connection here. Number one situation, as you see, it has two X-intercepts, distinct, not the same, which means that this quantity, which is called just this, not the square root, it's called discriminant. This quantity must be positive. So we take the square root and we get two options. Here there is only one common point. Basically there are still two solutions, but they are not distinct, they are the same. In this case, the discriminant is 0 for this situation. And here there are no X-intercepts, which means b squared minus 4ac is a number less than 0, which basically means that the square root of this number is not a real number. So here two distinct solutions. Here two solutions, so also real, right? Real solutions. Here two solutions, but we like to say one solution, which is also real. But here, no real solutions, imaginary, no real solutions. The same thing with a minimum. A minimum can have the same situation. Way above, no solutions, resting on the x-axis, one solution, and two distinct solutions. The same situation. The discriminant is the key. The discriminant tells us what solutions, what options we have. Also, if I know that the function has a maximum and the y coordinate is positive, it must be this. If the function has a maximum and the y coordinate is 0, it must be this situation. And if I know that there is a maximum and the y value is negative, then I know there are no real solutions. So the vertex tells us everything as well. Any questions? Any questions for me? Okay, the next step then, I'd like to look at absolute value functions. They're nice functions also. They're defined on all real numbers. So this is the simplest possible absolute value function. And I'm hoping you remember the graph. It's like a V at the origin. Bisects the first quadrant into two equal parts, of course, and the same with the second quadrant. So this is the absolute value of x. Now, knowing transformations, we can graph anything quickly. Yes, we may not know the x and y intercepts, we may have to determine them algebraically, etc., etc. But now we can have a very good picture of something like this. Let's say 1/2 the absolute value of x minus 2 and plus 2. I know very quickly how this looks like. I don't need any calculator. I graph the base function, which is the absolute value of x. In order of operations, I have to shift the graph 2 to the right. This is the absolute value of x minus 2. Then I have to use shrink the graph by a factor of 1/2, no problem. This one so you can see it better. This is 1/2 the absolute value of x minus 2. And now all I have to do is move it up 2. So the purple graph goes up 2. So it's this. So I know exactly how it looks like. I know the domain is all real numbers, and I know the range now. So this point is at positive 2 up 2. So the range of this function is 2 to infinity. It doesn't have x-intercepts. Can I determine the y-intercept? Yes, no problem. I only have to determine f of 0. 0 minus 2 is negative 2. The absolute value is 2. Divided by 2 is 1. 1 plus 2 is 3. So 0, 3 is this point. So see how useful transformations are, really. Okay. There are also examples of radical functions. So let's also graph at least one square root, so we refresh our memory on how to graph the square root. So square root now. The simplest possible square root, of course, is this. And let's say we want to graph a function f of x equals the square root of x plus 3. We know what this does to the graph, but let's graph the square root of x first. The domain of this function is greater than or equal to 0. All x values that are greater than or equal to 0. So domain 0 to infinity. So I'm hoping you remember this graph from your past experience is something like this. It's not a straight line. So this is the square root of x. Now for this function, for the square root of x plus 3, I have to write that this quantity is greater than or equal to 0 now. And I move 3. So then the domain of this function is negative 3 to infinity, as I expected, because the graph shifts to the left 3. And here it is. So this is the square root of x plus 3. Very easy to determine the range for both, of course, 0 to infinity, from the smallest y value till the largest y value. Any questions? Any questions? Okay, when we talk about polynomial functions, not linear and not quadratic, polynomial. But you can say linear function is also polynomial, I agree. But we graphed those in the previous section. You can also say quadratic. I agree. Quadratic function is a polynomial function, but we just finished that. So when we really talk about polynomial, we say degree, 3, 4, 5, etc. Degree. So a cubic function, a 4th degree function, a 5th degree function, etc. So let me give you just a shortcut of what they really mean. So an odd degree and an even degree. Of course, polynomial functions. An odd degree polynomial function behaves like a linear function. It can come from negative infinity, do something, and go to positive infinity. Or it can come from positive infinity, do something, and go to negative infinity. All odd degree polynomial functions follow this. I don't know how many terms, it depends on the degree. Or follow this. From negative infinity to infinity. Or from positive infinity to negative infinity. When is this and when is that? Of course, the leading coefficient. If the leading coefficient is positive, it does this. If the leading coefficient is negative, it will do this. All polynomial, odd degree. Now for even degree, they behave like the quadratic function. They either do this or do this, like x squared or negative x squared. Of course, the leading coefficient is positive here, and of course the leading coefficient is negative here. This one, of course, comes from positive infinity and goes back to positive infinity, and of course this one comes from negative infinity and goes back to negative infinity. That's really the entire theory. There is really nothing else. Odd, similar to the linear function. Even, similar to x squared or negative x squared. Well, depending on the degree, it will have more terms or max min or less. Okay, any questions? So I reached my note, I don't want to forget, directly and inversely proportional. And then I'll stop because I would like us to work on something. So directly proportional. When we say y is directly proportional to or with x, we mean y equals k times x. K is a constant of proportionality. Constant of proportionality. If we have the inverse, inversely proportional, then the relationship is y equals k over x. Of course, k is still the constant of proportionality, and when we hear or see or read y is inversely proportional to x or with x, then we have that situation. And keep that in mind because it will pop up. What else I have to refresh our memory on are rational functions, exponential functions. I don't see any log here. They will come in later, so the log functions are coming in later. I have to refresh our memory on exponents. That's a big issue, very important. Finding more domain. And then looking at business and economics applications about demand and supply. And that will be the end of R, but we still have some way to go. Okay.